Good morning to everyone. I hope you all are doing well. We have been talking about this concept for the last couple of lectures, and we have discussed different examples. So today we're going to talk about another type of hybridization, and we will explain this type of hybridization with the help of some examples. So today we're going to discuss Sp3d2 hybridization. Before this, we have discussed simple hybridizations involving S and P orbitals like Sp, Sp2, and Sp3. And then in the previous session, we talked about Sp3d hybridization. Today, we will discuss Sp3d2 hybridization. And we will do this with the help of some examples. So the first example is that of SF6. Let's see how SF6 is formed and what will be the hybridization of sulfur, or how we can determine the hybridization of sulfur in SF6. Now, as I told you earlier in the previous session, that in such molecules we have a central atom. So the central atom in this molecule is the sulfur atom. Sulfur, you know, it belongs to the 6th group, right? And it lies under oxygen. Its atomic number is 16. If you write its electronic configuration, that is 1s2, 2s2, 2p6, 3s2, 3p4. So this is the electronic configuration of sulfur. And you can see that because it lies in the 3rd row after oxygen, below oxygen in the 3rd row, so the valence electrons, they lie in the 3rd shell. And in the 3rd shell, you know that we have the 3d orbital as well. In case of sulfur, it does not have any electrons present in it. Looking at this electronic configuration, you can see that this sulfur has 6 electrons in the outermost shell. We discussed the same atom in case of SF4 in the previous session. The valence shell electronic configuration of sulfur is 3s2, 3p4. If you write it in this way, you start filling these p orbitals singly first. And because we have 4 electrons, one of them would be paired up. Looking at this electronic configuration, or the valence shell electronic configuration of sulfur, we have only 2 unpaired electrons. And for that matter, you would expect this sulfur atom to form 2 bonds. In fact, in case of SF6, it is forming 6 bonds. How would it form 6 bonds? That is by the promotion of electrons into the 3d orbitals when it gets energy, right? So let's see what happens. So if we have these 5 3d orbitals, one of the electron from the 3px here is excited into the higher energy 3d orbital. So now we are left behind with an unpaired electron in the 3px and an unpaired electron in the 3d orbital. So how many unpaired electrons we have now? 1, 2, 3, 4. Right? So now we have 4 electrons, unpaired electrons. And that was the case in case of SF4. But now we have SF6. It means that we need 2 more unpaired electrons. So you can see here, we have another pair in the 3s orbital that could be excited into another 3d orbital. So this electron in the 3s will be left unpaired. This will be unpaired, single. This is already, these 2 are unpaired. And we have single electrons in the 2 3d orbitals as well. Right? So what we have now is 3s1, 3px1, 3p-Y1, 3p-Z1, and we have 2 electrons here in unpaired form. Now we have 1, 2, 3, 4, 5, 6 unpaired electrons. And this is known as the doubly excited state or the double excited state of sulfur. In the previous case, in case of SF4, we had excited only 1 electron from the 3p orbital into the 3d orbital. But in this case, 2 electrons are excited into the 3d orbital, one from the 3px and the other from the 3s orbital. Right, so it's a double excited state. Again, as I've mentioned before, if you allow these fluorines to form bonds with these 6 orbitals, we have 6 orbitals with unpaired electrons. So the bond angle, the bond lengths would be different, the bond energies would be different. So what happens is that these 6 orbitals, they hybridize together, they are mixed together to form 6 new orbitals. The 6 new orbitals will be produced. Okay. And we have how many? 1, 2, 3, 4, 5, 6 electrons. So each of these orbitals will get an electron. And these orbitals, which now have equal energies, are known as the Sp3d2 orbitals. Right? You can see here there is 1s, 3p, and 2d orbitals, so a total of 6 orbitals should be formed at the end, and that is what we have. And now 6 fluorine atoms can bring their electrons, their p electrons, and combine with these 6 electrons to form SF6. Let's see how that is done. Okay, so we have the central atom, that is S, and it will combine with 6 fluorine atoms. Now, when fluorines are coming in to form bonds, they would tend to be at maximum distance from each other. What happens is that these orbitals, these Sp3d2 orbitals, also tend to be at maximum distance from each other. And this is how they are arranged. And then fluorines will bring their electrons in the p orbital bonds with each of these orbitals. Okay, so let me draw it with bonds rather than the orbitals. So we have the central atom S. It's going to form 6 bonds. It has 6 orbitals. They are arranged in this fashion. Now, what is the actual orientation of these orbitals? You see, we have 6 orbitals, and again, they tend to be at maximum distance from each other. So these 4 orbitals, here, they are on the horizontal plane, right? So they are again on the horizontal plane, as we had discussed in the trigonal bipyramidal geometry. These 4 orbitals are on the horizontal plane, and these 2 are on the vertical plane. So these 4 orbitals are horizontally placed, and these 2 are vertically placed. You can connect them in this form, right? And so they are horizontal, and each one has a fluorine atom. These 2 also have fluorine atoms. Now what happens is that these fluorines, if you can also connect this bond with all of these 4, like this, and you can now see that they are pointing towards the corners of an octahedron, right? So it can form an octahedral geometry. We have the formation of an octahedron. Octahedron means that it has 4 faces above the plane of this horizontal axis and 4 faces below. See, this is one face, this one. This is the other face, this one. This is the third face, and one is behind the board. So we have 4 faces here, and similarly, you can draw 4 faces here as well, right? So you can connect them. You will have 4 faces below this horizontal plane as well. So that is why the geometry is octahedral. So it has an octahedral geometry, right? And this is the geometry of the molecule as well. So this was SF6 with Sp3d2 hybridization. Let's see another example. Okay, if we have an iodine attached to 5 fluorine atoms, that is IF5, what would be the hybridization and how would the molecule look like? Let's see. Again, we assume that this iodine has Sp3d2 hybridization to accommodate 5 fluorine atoms in this case. Iodine, we know it belongs to the 7th group, and in the 7th group, the elements have 7 electrons in the outermost shell. So it is in the 5th row, the outermost electronic configuration, outermost shell electronic configuration would be 5s2, 5p, 5, and 5d, 0. Let's see what happens. We have the 5s2 electrons, and then we have the 5px, 5py, and 5pz. So we have 5 electrons in the p orbital. 1, 2, 3, 4, and 5. And then the 5d is empty. We do not have any electron in the 5d. Now we have to accommodate 5 fluorines or 5 atoms from outside with iodine, but here you can see that it has only 1 unpaired electron. So electron have to be excited from this p orbital into the 5d. This is the 5d orbital. One of the electrons is excited from this pair into the 5d orbital, leaving us with 1, 2, and 3 unpaired electrons. So then we have to excite another electron from the other p orbital into another d orbital. And now you can see we are left with 1, 2, 3, 4, and 5 unpaired electrons. So again, it's a double excited state, or it's a doubly excited state of iodine. So what we are left behind with is 5s2, 5px1, 5py1, 5pz1, and then we have 1, 2, 3. We have 2 electrons singly occupied by the 2 5d orbitals. And now you can count 1, 2, 3, 4, and 5 unpaired electrons are there, and so 5 fluorines could be accommodated now. But because these 5 electrons are in different orbitals, they need to be mixed together along with the 5s. So we have 1, 2, 3, 4, 5, 6 orbitals mixing together to form 6 Sp3d2 orbitals. So 1s, 3p, and 2d orbitals are involved to form 6 Sp3d2 orbitals. But in this case, how many electrons are there? So we have 2, 3, 4, 5, 6, and 7 electrons. In the previous case, we had 6 electrons, but now we have 1, 2, 3, 4, 5, 6, and 7 electrons. You start filling them singly, 1, 2, 3, 4, 5, 6, and one of them is paired up. So again, we have 6 orbitals, Sp3d2 orbitals, but 5 of them have single electrons, one of them is paired up. And because we need to accommodate 5 fluorine atoms, this fits perfectly. Let's see how will the bonds be formed. So again, these 5 fluorine atoms, they would tend to be at maximum distance from each other. We also have a pair, and this pair, is not involved in bonding with fluorine. जब आपके पास paired electrons हो तो bond formation में involved नहीं होते हैं, सिर्फ जो unpaired electrons हैं वो involved होते हैं bond बनाने में, ठीक है? So what about the pair? This pair is not going to form any bonds with fluorine. It will be present as a lone pair on iodine. But again, we have 6 orbitals, so we have to accommodate these 6 orbitals in the space with maximum distance from each other. So again, we have 1, 2, 3, 4, 5, and 6. So we have these 6 orbitals accommodated in space with maximum distance from each other. And if you look at this geometry, it again is an octahedral geometry. But in this case, we have to attach 5 fluorine atoms, right? So those fluorine atoms bring their electrons and share with these single electrons, 5 of them, 1, 2, 3, 4, and here is the 5th one. What about this orbital? We have filled in 5 fluorine atoms. We do not have any other. And we have used up 5 sp3d2 orbitals. The 6th one has a pair of electrons. And that pair is present here in the form of a lone pair. Alright? So again, if you look at the overall geometry of the orbitals, it's an octahedral geometry. Because again, the hybridization is sp3d2, right? And you can connect them to form an octahedron. But when you draw the molecule, you would see, because in the molecule we do not draw lone pairs, so we only have the bonds like this. Okay, one thing you should remember is that again, because it's an octahedral geometry, these 4 orbitals, 1, 2, 3, and 4, they are in the lying in the horizontal plane or axis, and these 2 are on the vertical axis, perpendicular to these 4 orbitals, right? So again, we have these 4 orbitals which are on the horizontal axis. This one is perpendicular. Here we have the lone pair. So let's see what would be the geometry. These 4 are in the horizontal axis, and we have this fluorine atom present vertically to these 4 fluorine atoms. You can connect them here. And you see it again forms a pyramid-like structure. So it's a pyramidal structure. It's different from the one we have discussed already, that is trigonal pyramidal. It's not trigonal. It has 4 corners. It's not trigonal. It's square. And it's not bipyramidal. In trigonal bipyramidal, we had a pyramid above the triangle and we had a pyramid below the triangle. But here we do not have a pyramid here. We only have one pyramid. So it's square pyramid. So this is how IF5 is formed. Okay, let's move on to the third example. Remember, in SF6, we do not have a lone pair. We have sulfur with 6 fluorines attached. In IF5, we have iodine with 5 fluorines, but now we have a lone pair. Let's see an example. We have xenon tetrafluoride. Now this is interesting. Normally we say that the noble gases, those that belong to the group 8, do not form bonds, but actually some molecules have been even synthesized, or they have been seen. But usually the molecules formed by the noble gases, they are highly unstable. The elements that are on top, that is helium, neon, argon, that they are least reactive, and the one lying in the 4th, 5th, 6th row, that is xenon, krypton, they are mostly reactive, so they can form bonds with other elements, right? Let's see the electronic configuration of xenon. Again, it belongs to the fifth row. So, the valence shell electronic configuration will be 5s2 by px2 by py2 and by pz2. Xenon has 8 electrons in the valence shell because it belongs to the group 8, so it has 8 electrons in the valence shell, and you can count them here. And then we have the 5p orbital that is empty. But again, looking at the electronic configuration, you would think that xenon cannot form any bonds because it does not have any unpaired electron. But here in this molecule, it has attached 4 fluorine atoms. So when xenon is going to form bonds with 4 fluorine atoms, again, electrons are going to be excited. So let me draw these 5d here. Again, 1, 2, 3, 4. So one of the electron is promoted into the 5d orbital, and from the one of the p orbital, and then another electron is promoted from another p orbital into another g orbital. Right? So what we have now is 5s2, 5px2, 5py1, 5pz1, and then you have the 5d orbitals with 2 orbitals having single electrons. Right? So now we have how many? 1, 2, 3, 4 unpaired electrons, and xenon is going to accommodate 4 fluorine atoms. So this fits perfectly. How many electrons do we have? 2, 4, 5, 6, 7, 8 electrons are there. So we have to mix the orbitals, 1, 5s, 3 from 5p, and 2 from 5p to form 6 sp3d2 orbitals. Now, how many electrons do we have? We have 8 electrons to accommodate. We have 2, 3, 4, 5, 6, 7 here, and here goes the 8th electron. So we have 1, 2, 3, 4, 5, 6, 7, 8 electrons here. Right? And you can see now that we have 4 unpaired electrons that can accommodate, and they can bond with 4 fluorine atoms, and we have 2 pairs of electrons. These pairs will not be involved in bonding, and so they will be present as the lone pairs. So we would have xenon here with 4 fluorine atoms, or 4 orbitals which have single electrons, and 2 here have pairs. Now these have to be at maximum distance. Now you can imagine, according to Westphal theory, if you remember, there's repulsion between these electrons. So we have bonded electrons, we have non-bonding electrons, and you can see that, or if you remember, that the non-bonding electrons, they exert even more repulsion in this case, right, than the bonding. So we have these 6 orbitals oriented along the corners of an octahedron again. But where do we fit the fluorines and where do we fit the lone pairs? These fluorines tend to be at maximum distance from each other, and so they are present on the horizontal axis, the 4 orbitals on the horizontal axis. These 2 are the orbitals on the vertical axis. So your lone pairs would like to be present here on the vertical axis to have maximum distance. Now you see that they have 90 degrees angle with all the xenon fluorine bonds, and now you can see that again it has an octahedral geometry. You can form the octahedron like this, okay, and 4 faces on top and 4 faces below, so it forms perfect octahedron. Right? What would be the geometry of the molecule? So we have xenon with 4 fluorine atoms, and they would be placed like this. We do not write the lone pairs here. So you can see, as I told you earlier, that these 4 fluorines or the orbitals with which fluorine bonds are present on the horizontal axis. So all of them are in the same plane. So they are planar and they form a square. So the geometry of the molecule is square planar. Right, so xenon fluoride will have a square planar geometry because all of these fluorine atoms, they are in one plane. So this is how sp3d2 hybridization takes place in different molecules. And then you can see that these molecules, they have different geometries. एक सिंपल आप चीज देखें कि यहाँ पर हमारे पास एक S, 3P और 2D orbitals है. So we have 1S, 3P and 2D orbitals. So total is equal to 6. And that means that the central atom will have 6 things attached to it, or it will have 6 things around it. Those 6 things could be bonding electrons, or those could be non-bonding electrons. So in case of xenon fluoride, you see it has 4 fluorine atoms. It means there are 4 bonding pairs and 2 non-bonding pairs are there. Right? So 2 lone pairs are present here. So we have 4 bonding pairs, 2 non-bonding. So a total of 6 is there. If in case of SF6, the central sulfur atom has 6 fluorine atoms attached to it. So it has 6 already. So just by looking at the hybridization, you can predict, or you can tell how many things would surround the central atom. In case of sp3d, you would have 5 things around, or 5 bonding or non-bonding electronic pairs around the central atom. In case of sp3, we have 4, sp3, we have 3, and so on. Right? So thank you so much. This is all about hybridization. In the next lecture, we will start another topic.